Okay, welcome and welcome back. Alan will open the series about the g-conjecture and beyond.
Okay. Thanks for the invitation to speak, and is it good? And thanks to June and Dave for organizing, inviting me to come and organizing the whole special year here. It's been fantastic. So I took a break from doing maths for about a decade, and I started doing math again after COVID, and I was very interested in hearing about all the things that I'd missed out on because I hadn't been paying any attention. And Karu told me that he was thinking about this result of these two Greek mathematicians called Papadakis and Petrotou, and he told me that this was the biggest result in Stanley Reisner rings for the last 40 years. So with the caveat of maybe not being an absolute expert, today I want to give a mainly expository talk explaining to you what that result is. And then at the very end, I'll talk about some joint work with Matt Larson, who's here, and some other people. Okay. So to explain their result, I need to tell you the motivation, which was that they solved, it provides a proof of a conjecture called McMullen's g-conjecture. Which was made in 1970. Okay. And I'll tell you what it is very roughly first. So this is a classification of all the possible F vectors of simplicial spheres. Okay, so what does that mean? So throughout this talk, so delta is going to be a simplicial complex it's going to be D minus one dimensional with vertex set. So I'll give an example in a sec. A vertex set V, which I can label 1 through n. So I have n vertices. So there's two ways of thinking of a simplicial complex. We can think of it as a bunch of simplices. So if I have a zero simplex, it's just a bunch of points. This would be when D is 1. If D was 2, this is a one-dimensional simplicial complex. It might look something like this. So it's a bunch of simplices glued together along common faces. When D is 2, it might look something like this. Okay. And there's two ways of thinking of a simplicial complex. I can think of it as simplices glued together, and then I have the notion of thinking of this as a topological space, well-defined up to homeomorphism. Or I can think of this as an abstract simplicial complex, that each of these simplices, because each of these simplices is determined by the vertices it contains. So I can think of the simplicial complex as a bunch of subsets of V. Okay, and that's an abstract simplicial complex. And for this talk, the thing that I need is F sub I is the number of faces of the simplicial complex whose size, and by size I mean the number of vertices they contain, is I. Okay, so for example, F sub 0 is the number of faces with no vertices, and that's just going to be the empty face. So there's always F sub 0 is 1. F sub 1 is the number of vertices. which I called n. F sub 2 is the number of edges, like this, and the F vector is just the vector F0, F1, and the biggest one is F sub D, because it's D minus 1 dimensional. Okay, so I'm going to have a running example over here. Just take one example. So here D is going to be 2, so it's 1 dimensional, and delta is just like this. And the F vector is 1, and there's 4 vertices here. 4, and there's 4 edges, so it's 4. Okay. And the last thing to tell you is that to be a simplicial sphere is the condition for a simplicial D minus 1 dimensional sphere means that, so I'll write this just to mean the simplicial complex as a topological space is homeomorphic to a sphere of dimension D minus 1. So that these ones that I drew here are all spheres. Okay. So, okay. And this one here is a sphere. And so McMullen, the conjecture is a conjectural classification of all possible F vectors you get from simplicial spheres. Okay. Now I'm going to state the actual conjecture here, and I'm not going to explain what it means. I'm mainly just going to tell it to you now because it's a little bit funny to state it. But and then later in the talk we'll understand what this means. So what's the conjecture of F vectors? It's the G vector of the H vector of delta is an M vector. So it's kind of a little silly. And every M vector occurs. Okay. So I will explain what this means later. I just thought it sounds silly, so I just say it now. Okay. All right. I want to tell you a little bit about the history. So the first really big result in this direction was in 1979 by Stanley, Biller, and Lee. So they showed that this conjecture is true in a special case called the polytopic case. So polytopic means that my sphere looks like it's naturally the boundary of a polytope. So notice in all these examples I gave you here, this is naturally the boundary of a polytope. Yeah, this one too. Okay. And when D is at most 3, every simplicial sphere has this can be realized in this way. So this is all examples. But unfortunately, when D is 4 or bigger, Kalle proved that if you fix D and you let this n, the number of vertices, go to infinity, then the proportion of simplicial spheres which are polytopic actually goes to 0. So in general, it's a small proportion of all spheres. Now, this was like one of the big results in combinatorics last century. So Biller and Lee's contribution, the they were responsible for this sort of part, which is like the sufficiency. And Stanley was responsible for this necessity condition. Okay, and the way he did it, which we will see, I will touch on, is via algebraic geometry and something called the hard-Lefschetz theorem, applying the hard-Lefschetz theorem. Okay. Now, if you're away from this special case, the algebraic geometry breaks down, but people worked on this very hard, and I'm not going to talk about this, but you can imagine this led to a lot of mathematics, a lot of special cases were proved, and it's all summarized. You can read, there's a very nice survey article called 35 Years and Counting, which summarizes all this by Schwartz. And as an exercise, you can check, this was written in 2014. There's a theorem that says that if you take the number 1979 and you add 35 to it, that you'll get the number 2014. Okay. But nobody was really very close to solving the problem in general. And then in 2018, Petrotou announced a proof, kind of out of nowhere. Petrotou. So this was a very big deal. Like very roughly, the algebraic geometry breaks down, but the underlying commutative algebra, the proof is very vaguely a commutative algebra proof. And then in 2020, and this was what I was referring to before, a different proof was given by these two mathematicians, Papadakis and Petrotou. And just very quickly, they worked in characteristic 2, and they proved something called, so this is what I will talk about in this talk. They proved a property called anisotropy of a quadratic form. And if you know about sort of the algebraic geometry, in algebraic geometry of hard-Lefschetz theorem, something called the Hodge-Riemann relations, this anisotropy can be thought of as a replacement for the Hodge-Riemann relations, but you're working in characteristic 2.
A bit bigger.
Yes, sorry. Okay. And then the last thing, in 2022, this is Kalle, who I talked to, and Xiao. They strengthened Papadakis and Petrou's result and greatly simplified it as well. Okay. So now I want to talk about the statement. But if you don't know anything about simplicial complexes and you want to take like one thing out of the talk, like we want to remember one thing, it's so Mel-Hochster, Stanley, Reisner, and many other people, they developed like a bridge that goes between simplicial complexes and studying their topology and commutative algebra. And this is like the key to studying a lot of things in simplicial complexes, but especially this problem. Okay. So there's a bridge. So anything I say about simplicial complexes and topology, Hochster and Stanley and Reisner say there should be some corresponding statement in commutative algebra. Okay, so how does this go? So in our case, let's take the different pieces of the theorem. So I have a simplicial complex, and its dimension is d minus 1. Okay, then the corresponding thing in commutative algebra is something called the Stanley-Reisner ring, okay, which I mentioned at the start, or it's sometimes called the face ring. and this will have Krull dimension D. Okay. So here, to describe what this is, I'll tell you what this is. So here K is a field. And recall that my vertex set I labeled, I'm probably not writing much bigger, sorry, I just go back into the habit. My vertex set was 1 through n, so what is this ring? You just take a polynomial ring indexed by the vertices. And then you quotient out by an ideal. And the ideal is you take any subset F of the vertices that does not, I don't know, maybe you can't see that. Yeah. Okay. Let's call this I delta. So I take a subset of V, which is not a face of the simplicial complex, and that will give me a square-free monomial. I take the product of all vertices of F, x to the V. So it's easiest just to see this in action in an example. So in this running example, I have 1, 2, 3, 4. And so my Stanley-Reisner ring is K, x1, polynomial ring in 4 variables. And anytime I have something that's not a face, I quotient out by a monomial. So here 1 to 3 is not an edge. So that means I quotient by x1, x3. And x2 to 4 is not an edge. So I quotient by 2, 4. And those are my minimal non-faces. So that's my Stanley-Reisner ring. Okay. So let's just go down the list of things. So we also talked about this F vector. So the dictionary says the F vector has to correspond to something in commutative algebra. So what's that? So here I want to assume that my ring here is something called Cohen-Macaulay for this, what I'm about to say to be true. According to this logic, a property of a ring should correspond to a property of a simplicial complex. So this is also true here, but it's not important for the talk. Being Cohen-Macaulay about means that if you look at the simplicial complex and you look at the link of any face and take cohomology, that cohomology is sort of concentrated in the highest degree possible. This is something that is true for spheres, so this property will be satisfied for spheres. Okay, if you have something called Macaulay, and let's say K is infinite, which it will be for us later, then there exists a system of parameters which consists of things in degree 1. Okay, so my Stanley-Reisner ring was a quotient or polynomial ring, which is graded. So it makes sense. So the quotient will still be graded. It makes sense to talk about linear things. But very concretely, I'm just saying to be in degree 1 is saying that my theta I is some sum between j equals 1 and n of some coefficient aij times my variable xj. And now if I quotient by this, So define H of this guy to be my Stanley-Reisner ring modulo theta 1, theta d. I can always do this so that this guy is finite dimensional. Okay, I didn't really use Macauliness here, but anyway. And this sequence is called a linear system of parameters. But the point here is that once I have this ring, this is called an Artinian reduction of my ring. So I just hit it by things until I get something finite dimensional. I knock its Krull dimension, which was D. I knock it down till it gets to 0. And I've got something finite dimensional. Once I have this ring, I can take a Hilbert series. Remember, I was looking for a vector. So now I can go back and I can take the Hilbert series. Oh, sorry, I'll just write it here. Okay, and now that should correspond to something about simplicial complexes, and it's almost the F vector. So it's actually something called the H vector, okay, which appears in our statement of McMullen's G theorem. And the H vector, but the H vector and the F vector are the same up to some transformation, which is unimportant for understanding things. So if you tell me the H vector, I can tell you the F vector and vice versa. So these guys are equivalent. Okay. So this is how our dictionary works here. So rather than defining the H vector, I'll just tell you what it is in this case. So the H vector is 1, 2, 1. Okay. And what's my ring here? Well, I need to tell you what these things that I smash it with are. And I've got a choice to make, but I'll just make a really easy choice. So I could take my theta 1 to be this, my theta 2 to be this. Okay. And now if I quotient by this, just setting x1 to be x3 and x2 to be x4, then what does this ring become? It does become finite dimensional. x1, x2. And then these relations become just x1 squared, x2 squared. Okay, which is finite dimensional. And it has a basis 1, x1, x2, x1, x2. Okay, so the Hilbert series of this is this vector here. Okay. Now,
The theta is supposed to satisfy certain property.
they're meant to be linear, and they just have the property that it's a system of parameters, which means that when I quotient by this, I get something of that's finite dimensional.
And then the Hilbert series is independent.
No, the Hilbert series is not independent, so this is a very good question. So traditionally, I don't write theta here in this notation, but that's a really bad thing to do. So the theta is actually very crucial. I'm only really following the historical convention of not putting theta in this notation to save time. But yes, a priori, everything depends on theta. In this case, actually, because we have a sphere, this H vector doesn't depend on theta because it's just counting things in the simplicial complex. It doesn't know about anything I did here. So in this case, in the end, my result, that Hilbert series is independent of the choices I make. Does that make sense? But for a long time, people thought it wasn't important. But actually, in what follows, we'll see it is very important. Yeah. Okay. So I should say that this is like, in this example, oh, I can't do it. So this is the cohomology ring of P1 cross P1. Okay. So this, in the Stanley's case, in the polytopic case, you'll always get something like this. This H of delta will be a cohomology ring of a projective toric variety, which is something called quasi-smooth. Okay. So we're just working our way through our dictionary. What were the other things we need to translate? Well, we had the fact that as a topological space, we had a sphere. That should mean something in commutative algebra. So this condition implies that something stronger than Cole-Macaulay, it's that this ring is something called Gorenstein. And what that means for us is that if I take, so I'm going to index the degree up here because it's indicating it's like cohomology. So the top degree piece here, it says is in degree D, and that this Gorenstein is going to imply that that is one-dimensional, and that Poincare duality holds, which means that if I'm in degree I and I multiply by something in degree D minus I, so that I get something in degree D, that this is non-degenerate. Okay, so it's saying the I piece and the D minus I piece are dual to each other. So in particular, this means if we go back to simplicial complex land, this means that the H vector, because the H vector in this case is the Hilbert series of this guy, the Hilbert series is symmetric. Okay. Okay, so the last piece of my dictionary is that I want to tell you, so we've kind of translated everything. So what does the g-conjecture itself mean in commutative algebra? So this should correspond to something in commutative algebra. Maybe this isn't quite bijective, but there should be some corresponding thing here. And the corresponding thing here is called the algebraic. So I'll try to write bigger. The algebraic g-conjecture. So this was the actual thing that was proved, and it implies McMullen's g-conjecture. And it states that there exists a choice of K, my field, and a choice of my linear system of parameters, so that this ring has a Lefschetz element. Okay, and what does that mean? An element, a linear element, so an element in degree 1 is called Lefschetz if there's two different ways of saying it. There's the non-confusing way and the confusing way. So I'll start with the non-confusing way and then try to confuse you. So it's Lefschetz if for I less than half, multiplication by L to the D minus 2I gives an isomorphism from here to here. So what I'm saying is here I have the ith graded piece. I have a linear element. If I multiply by this, I keep pushing up the degree. So I go from degree I to degree I plus d minus 2i, and I land in here, okay? Now we know that these two spaces are duals to each other, so they have the same dimension, and the left Schertz element means you have an explicit isomorphism, which is take an element here, multiply it by this element, land in here, that's an isomorphism. And then there's an equivalent way of saying it. So this is like if and only if. So it's a little linear algebra exercise that these are the same. But if I wanted to present this in a more confusing way, you could also say that you could define a pairing from HI cross HI to HD. So I wanted to mention here, I should have said it before, but this guy is isomorphic to K. There's actually a natural choice here. There's a natural isomorphism here by Brion. So I'll call this map DEG. So we use Brion's choice. That's not important for what I'm saying here now, but I can define a form which takes x, y, and I multiply them, which will get me into degree 2i, and then to get into degree d, I can multiply by d minus 2i, and then I can take this isomorphism. Okay, that's going to be a bilinear form, and equivalent to this being an isomorphism is that this guy is non-degenerate. Okay, so non-degenerate means if I take a non-zero element here, there exists some element here which pairs non-zero, has a non-zero pairing with it. Okay. And why does this solve the g-conjecture? So if you knew that this existed, then, not sure where to write, but sorry? Yeah. Yeah, so we solved this. If you solve this one, you solve the other one. We don't know what the other one is, but we solved it. So if you knew this left Schertz element existed, yeah, what would this imply? Now we go back to the world of simplicial complexes. It would mean that if I look at the vector, if I define gi to be hi minus 1 for I equals 0 up to halfway, that this is the Hilbert series. So the g vector, that's the second thing I mentioned, is this g naught up to g d over 2. If there was this left Schertz element, then this guy would be the Hilbert series. Of, in our case, it would be of this ring modulo. Well, I guess I didn't quite prove it, but you can convince yourself that if you knew that was true, then if you took the Hilbert series of this H killed by the ideal generated by L, that Hilbert series exactly records these differences. Yeah, so on the way, in the first half, your multiplication by L is injective, and the second half, it's always surjective. Okay. And so like a definition, an M vector is a Hilbert series of graded ring so let me just say it. This is the last thing in my statement. An M vector is a Hilbert series of a graded ring satisfying the conditions that in degree 0, it's just the underlying field. A is finite dimensional over K. So it's just the Hilbert series is just a sequence of numbers, finite sequence of numbers, and that A is generated in degree 1 as a K algebra. Sorry, but okay. So M is for Macaulay. So Macaulay classified these. So I could have, this is like the commutative algebra definition. There's a few equivalent definitions. There's a purely combinatorial definition, which I'm not going to give you. It's a little unenlightening unless you know how Macaulay proved this. But these things, M vectors are totally classified by Macaulay. You can see that there's some, the flavor of it is like if you know that your algebra is generated in degree 1, you can't have too many elements in degree 2. Okay, or like it bounds the number of elements you can have in every degree. Okay, but this is a problem solved by Macaulay in like the 1920s, was classifying these, and this completes now this shows that algebraic g-conjecture implies this statement I have above, that the g vector is an M vector because it's the Hilbert series of some algebra.
Question?
Yeah.
Well, this viewpoint of commutative algebra on the
Uh-huh.
problems with the base set. So how do McMullen conjecture this strange conjecture? If you didn't have it, how do you ever conjecture such a thing if you don't have to use algebra to begin?
Well, yeah, I'm not sure. I don't know. This is this caveat that I'm not an expert in the history of it.
I read that paper once, and actually many people after that conjecture appeared were very surprised about how he actually came up with the conjecture, because what he did is write the inequalities that these M vectors satisfy. So that's the theorem of Macaulay that characterizes M vectors and the inequalities. They're very complicated, and McMullen conjectured those inequalities. So
Well, McMullen was not aware because then it doesn't call had already vector.
I think that the consensus is that he was not. Yeah. So Stanley actually said that it was a little bit outrageous that he even conjectured. So.
Wow. Yeah, that's kind of amazing. Yeah.
But not the both field plane. For example, could it be true that the statement for algebraic two field true for some, let's say, purely characteristic two, but not for C.
Well, I mean, I think like a priori, yes, definitely. I mean, Anisotropic, his proof works for any field. But like the Papadakis Petrotou result I'm going to talk about, it's very important that the field has a characteristic too.
For that proof. But
For the proof, yeah.
I'm just
Like
saying-
definitely, yeah. So this should be true for any field. Like the result should be true for any field. It's not going to be true for any choice of linear system parameters. You need to be careful about that. But yeah, it's not something, it's something that is true, yes, for any field. The proof I'm going to talk about is in characteristic 2. Yeah.
I guess you have an equivalence, right? Is it McMullen's conjecture equivalent?
No. Yeah, I kind of rubbed that one out. So it's this way. Yeah. Yeah. So this is a stronger statement.
Is there a stronger conclusion of simplicial complexes that you can get?
Just,
Going forward.
I mean, yeah, once we get beyond spheres. So that was one of the things I was going to talk about at the end. Okay. Oh shit. Okay, so now I can state like what did Papadakis and Petrotou, what was their result? So they said you take a field of characteristic 2, then there exists a field extension, which is going to be my big K, and there exists theta 1, theta d. So I'm going to tell you what these is. I'm just not telling you now for the sake of suspense. So that if I take L to be x1 plus x n, this just means the sum of the linear terms. There were n vertices that damn it, I erased it. Okay. So remember before I had this, to show that something was Lefschetz, I had this form. So I'll just write it again. I needed to show that this form was non-degenerate. So they proved something much stronger. They proved that this is anisotropic. Okay, and anisotropic, what it means is if I take an element of degree I, which is not 0. So if I was trying to prove non-degeneracy, I want to say that there's some element y which pairs with it and gives it something non-zero. That would be non-degeneracy. Okay, anisotropy is something stronger. It says that that element you can choose to be itself. Okay. So any non-zero element pairs with itself to give something non-zero. Okay. This is a really strong property. So for example, if you're working over the reals, like if you're working over the reals, then the corresponding property is being definite. So being either totally positive definite or totally negative definite. Okay. And in the algebraic geometry proof of this of Stanley, you have something called the Hodge-Riemann relations. Okay. And basically they say that in that case, this is just never going to hold. Okay. They say that you have definiteness on these primitive components of cohomology, but those primitive components are not the whole cohomology. This is like an analog of saying that the whole cohomology is definite. Okay. So, oh wait, I didn't want to do that. Oh, let me just say, like one consequence, like, is that if I take a non-zero element, then the square better be non-zero. Yeah, I is less, let me put a D onto it. Okay. By the definition, if the square was 0, this couldn't be true. So let's just check that this, like what happens in our example that I gave here. So here in this case, I have this ring, but you'll notice that x1 and x2, both squares are 0. Okay, so like either I've made like a horrible mistake or like I'm just demonstrating that this is something very unexpected because here it's just clearly false. And the reason this is not a contradiction is that the philosophy here is that the thing that went wrong here when you took the cohomology ring of a toric variety is that you made a very, very special choice of theta 1 and theta 2. Okay. But in this situation, what they want to do, and this is Anisotropic as well, is you want to take the most general choice possible. Okay, you just want to take a generic choice, and then you can hope for a statement like this. So what does that mean in this case? I had to choose these aij's to be some elements in K. How do I make a generic choice? One way you can make sense of this is you can say, okay, my big field K here is just going to be my little field, and then I adjoin formal variables, which I call Aij. I have this big transcendental extension over all my choices. Okay, and now this is a well-defined element in that field, and you can check that that this is a linear system of parameters. Okay, and under this condition, it's true. Okay, so okay, yeah, okay, and the proof is by yeah.
The AIJ is just not satisfying any algebraic relation.
Yeah, so these are I just pick algebraically independent elements and I could call them x1 through x to the nd, but I just call them Aij because it's convenient notation. And so I have some big field, and now I'm going to pick a linear system parameters. I can pick here any element of the field, and I just pick, my choice is I pick those variables that I adjoined. So in this example, I would adjoin like 8 variables because I have D is 2 and I have 4 vertices. I'd have Aij. There'd be 8 of those. So I'd take a transcendence degree extension of degree 8 of my field. Does that make sense? Yeah. The proof is that in this field K with all these elements Aij, you look at differential operators in characteristic 2 and you prove some identity, and yeah, not going to really explain it, but it comes down to proving you want to show that like this guy is non-zero. You applied a differential operator in a very, very clever way until you get something that you know is non-zero. Yeah, so I'm not really explaining that. It's very, very interesting and very mysterious. It's not very well understood. There was a lot of experimentation. From what I was told, there's a lot of experimentation in Macaulay too, which led to this, being able to prove this, rather than sort of some general framework. Okay. So now I want to talk about sort of some more recent work. So there was a conjecture, but so Petrotou, Papadakis and Petrotou in 21, they had a follow-up paper that I didn't mention where they combined their 2 approaches. One conjecture that they made in this was that, so we were working in characteristic 2, but you could ask what happens in characteristic P. So the conjecture was saying that if you take an element in degree I and say I times P is less than or equal to D, the conjecture is that if I have a non-zero element, then taking P powers should not be equal to 0. Okay. This is just saying that it's not 0 because the degree is too high. Okay, and then similar statement in characteristic 0. But basically, is what's going on a feature of characteristic 2, or is there some more general thing that happens in all characteristics? And the answer to this is yes. All the theory, there's an analog in all characteristics. And this was joint work with Matt and Kalle Karu. This was something we were working on last semester. So I just leave this as, I don't want to talk about it, but I just leave it as motivation, and you can talk to us about it or read about it if this inspires you. So another conjecture which came out of this theory was a very interesting conjecture called the odd multiplicity conjecture. So this was made by Papadakis and Petrotou, I think in 22. And so they said, okay, I have my delta, which is simply short sphere. And in McMullen's g-conjecture, you take the f vector, we classify the f vectors, but the f vector, it's a many-to-one mapping. Like many simplicial spheres can have the same f vector, okay? But what if we work on the commutative algebra side? So we have more information. Is it still a many-to-one map? So concretely, if I have a simplicial sphere, then this process is saying, so let me just be precise. They say if D is even, then I have a pairing from D over 2 to K. Sorry for the people who can't see, that's a K. I had my pairing which sends xy to be the degree of x times y. Because I'm in middle degree, the Lefschetz operator doesn't feature. So we know now that I'm in characteristic 2. We know now that this is anisotropic form, okay? And the conjecture was that this is now a one-to-one mapping, so that you can recover the simplicial sphere by there's a well-defined notion of a determinant of a quadratic form. If you take the determinant of this quadratic form, which is an element of k mod k squared, that you can recover it. Okay, and so this is also true. So that's also true. And this was joint work with Matt again, and Isabella Novik. Again, this was last year. And but actually deeming even kind of has nothing to do with it. I mean, well, what's true more generally was that, and this isn't a statement about spheres so much, but it's more general. It's, if you take an oriented manifold and you take any D and you take some index less than or equal to half, doesn't have to be halfway itself, then you can recover delta by taking the determinant from the determinant of the map, which I was calling this map. So yeah, if you think this is interesting, you can talk to us. I obviously not really explaining it very well, but this is kind of interesting. So like a special case is like when I equals 0, H sub 0 is one-dimensional vector space, okay? So this form is just a number. The determinant is just one number in K, and we don't know how to compute it. We don't know how to compute this form when I is 0, but we do know that it contains enough information to recover the simplicial complex, the simplicial sphere you started with. Okay. And then I just talk one more thing. So Petrotou, Papadakis and Petrotou, in their like joint paper, they went beyond spheres. And so, for example, they said that something similar holds if your simplicial complex is something called doubly Cohen-Macaulay. So a sphere satisfies this, but this is more general. I didn't maybe erase it, but the Gorenstein property that I mentioned before breaks down, but it's not too far from that. And this is kind of interesting for people because like if you have a matroid, like there's a lot of interesting examples of this. So for example, if you have a matroid, if it's co-loop free, then the independence complex of a matroid satisfies this. There's something called the Bergman complex of a matroid that satisfies this. And thanks to Luis and Afanasiadis, there's also something called the augmented Bergman complex of a matroid, which satisfies this. Okay, but there's interesting examples that satisfy this condition. And they basically said that even though before I was telling you that a Lefschetz element meant that multiplication from here into here was an isomorphism, this can't be true anymore, but they show that it's injective. And this answered a conjecture of Schwarz. And what it means is that in terms of the H vector is that you still have unimodality up to halfway, but you no longer have symmetry. So before hi was equal to h d minus I, but now you only have something called top heaviness, okay? These inequalities were known for the examples I just mentioned already, but yeah, but this is what they proved. And so, yeah. And so something that I've been working on with Matt, but we haven't quite posted it yet, so I guess 2025, was that even though in this case, again, I want the characteristic to be 2. Again, in this case, I don't have this Gorenstein property, but what we can show is that there exists a surjection so this guy isn't Gorenstein, but there's a quotient of it that is Gorenstein, and the Hilbert series of this guy, Gorenstein means this Hilbert series will be symmetric. So what is its Hilbert series? It's just going to be H0, H1 up to like halfway. And then it's symmetric. So the second half is just this one reversed. So, you know, these might be equal if it's even or odd. But, so what this is saying is that, so over here we see like, what does the Hilbert series of one of these guys look like? It like goes up towards halfway. And then in the second half, it's got this top heaviness. So it goes up and then it does something we have no idea in the second half. And that's kind of graphing the Hilbert series. Okay. And this guy, this is saying that this extra part here, this difference is like the kernel of something. So it's the Hilbert series of something algebraic. And then we can exploit that to get something I'll just explain. So then we can say, okay, if we want to study like this difference here, the differences that come here, we can say, just put in some notation, we can put in, call them this, and then we get some vector C, some C vector, which goes, I don't know, so approximately to halfway. And then using this, we can get a version of McMullen's theorem, which says that this C vector it says that this C vector is a sum of m vectors. So being a sum of m vectors is actually very close to being just an m vector. It's got a combinatorial definition which is almost identical to the combinatorial definition of an m vector. And every sum of m vectors occurs. So it basically is classifying what can happen in this part of these H vectors. And this technique also gives new inequalities for matroids. And yeah.
Like, your notation to look like HB minus I minus H I should be 0 based on previous one.
So this is for, sorry. Yeah, this is like, oh yeah. This is the Hilbert series of this guy, is this. But the original guy, yeah, this is for the original guy. Yeah. So it's basically, if you kill this part, what you're left with is something, up to reversing the order, you're left with something with whose dimensions are going to encode this number. Once you quotient, like the kernel of this map the dimensions will be these numbers. So then you can use the algebra to study those numbers. Sum of m vectors. Well, it just means I take two m vectors and I can add them component-wise. But let me say, I could, instead of saying a sum of m vectors, I could have said that if I replace the first entry by 1, C1, and keep the rest of them, that this is an m vector. I could have said that instead. So whatever combinatorial thing you had for an m vector, what's going on is that C0 the first entry can kind of be arbitrary, and then all the rest of the entries behave like they were part of an m vector. Okay, so I probably shouldn't have phrased it like this. It just makes it confusing. I could have phrased it like this. The condition is really on C1 through up to here, and you can kind of make C0 anything. And then this statement is basically that every m vector occurs this way. Yeah, okay, that's it.
One quick question. So you said that you, by proving this last statement, you get new inequalities for matroids. So another sequence that is known to be top-heavy is the winning numbers of the second kind. Have you checked those inequalities for winning numbers of the second kind?
I don't know exactly what you mean by that.
Take a matroid, count the number of flats according to its rank.
Okay.
It's known to be top-heavy. Form the C vector as you did. Is that an M vector?
In that sense. Okay. Yeah, I'm not sure. Well, I don't think we know that, right?
Yeah, I was asking just to try if,
For like rank 5 and 8, these inequalities are like very weak unless D is kind of large.
okay,
So
I see.
Yeah.
So what is mu in the?
So mu here is so like it's a general fact that So if you're in the doubly, so if you look at the top degree, this is no longer one-dimensional. It's always like isomorphic to the d minus ith homology of the underlying simplicial complex. If I didn't do this part of the dictionary because I skipped parts, but this is something on the algebraic commutative algebra side, and this is something on the simplicial complex side. And so mu, this is the dual to cohomology. So here mu is an element in cohomology, actually defined over the smaller field. Mu is going to be a generic cycle of the underlying topological space, which will give you a function, a linear function on top degree. And that linear function will induce something Gorenstein. Anyway, I didn't quite explain that, but that's what the mu is. It's a cycle of the underlying simplicial complex.
I just had a historical question.
Yeah.
So I don't know how cautious you were being with your wording, but you talked about Ali Prasito announcing a proof of the g-conjecture in 2018. There was another proof that was announced maybe a year earlier that turned out to be incorrect. And last there was no consensus about whether that 2018 proof is a proof. And I wanted to ask you if you know what the consensus is.
Well, I don't know. I maybe defer to you. I would say I don't really have any insight more to say what you said. I don't want to say anything wrong. But I would say that, I rubbed it out. But like the Papadakis Petrotou proof is when like Kalle, Karu and Xiao, when they simplified that, they really simplified. Like it's a very, very well written paper. And like that's been published and I've like read every word of it. It's definitely true. So I can just say that's definitely true. Yeah. Yeah.
Okay, let's take a 5-minute break and continue with glitch and stuff. Thank you.